We can use integration to find the volumes of shapes that are formed when we rotate an area on a Cartesian plane. This rotation can be about the x-axis or it can be about the y-axis. And to do this, you need to deduce an expression for what we call the differential element of volume. If you go to area, we also have a differential element of area. And when it comes to volumes, we have also what we call a differential element of volume. So the formula that you're going to apply depends very much on how your differential element of volume looks like. I'm going to explain two situations where sometimes the differential element of volume is a solid disk, and sometimes it looks like a washer where there is sort of like a hole in the middle of that disk. I'm going to explain the two situations and the kind of formulas that you're going to use for this. It's quite a very straightforward subject, but you need to have a little bit of imagination, especially when it comes to the kind of shapes that are formed. You just need to have a little bit of imagination so that you can choose the correct formula to apply. Most of these formulas actually you're given on your formula sheet. So I'm going to start with an example, which is a very simple example because the function that is going to be involved in this example is a straight line. I'm going to use a straight line. All right. But before I go there, I just want to highlight to you the steps that you have to take when you're doing this, when you're deducing the volume of an area, the volume of the shape that is formed when an area is rotated about the x-axis or about the y-axis. Now, so the first thing that you have to do is to sketch the area. You must be able to sketch the area, and then from there, you deduce an expression for the differential element of volume. So what we call a differential element is a small or tiny representative of the whole. So if we have a huge shape, we're just taking out a very small element, an infinitesimally small element, that will be sort of like a representation of the entire thing. In fact, we will be assuming that the whole shape is made up of these tiny differential volume elements. That is what it means. Now, once we deduce that, we can now integrate, which is essentially adding up all these small differential elements to find the volume of the entire shape. This is our approach. Sketch the area, deduce an expression for the differential element of volume, then integrate using appropriate limits. But we do this because we'll be doing it from first principles. But as time goes on, when we get used to this approach, we now know the formulas to apply, and we just take the formula and we apply it. So in this video, I'm just going to go back to first principles. Then I'm going to do another video where I'm just going to be applying the applicable formula, and you see how it works. It is quite a very straightforward subject, as I said. Now, let me give you now an example. So find, this is the question, find the volume of the shape formed when the area, so this will be an area that we're going to rotate. An area is 2D, and if we rotate an area about an axis, we get a 3D shape, which is the shape that has got volume. That, yes, it's a 3D shape, it is got volume. That is what we mean here. When the area bounded by y equals to 2x, x equals to 3, and the x-axis is rotated about the x-axis. So I'm going to have two situations here. One, we may decide to rotate that area about the x-axis, and to the y-axis. The y-axis. I'm going to have these two situations. So I said the first thing that we do is to sketch our area so that we see how the area looks like. And from there, we take it from there. This is a very important step, which is sketching this area. So let us do the sketch. I'm going to draw my axis. So I have the y-axis, vertical axis. I have the x-axis. No, let me not put it here. I have the x-axis here. Now from here I need to draw the line y equals to 2x, because we have three boundaries. We have three boundaries here. Let me use a green pen. So this is the line y equals to 2x, passes through the origin. There it goes. All right, let me make it small. I don't want to make it too long. So this is the line y equals to 2x, and then the other boundary is this line here. The x-axis is the other boundary. Stop here. Then the final boundary is the line x equals to 3. So I come here. This is my x equals to 3. So this is the x-axis. This is the y-axis. So this is the point x equals to 3. This is the, I'm going to draw it like this, a dotted line. So this is the area that we need to rotate, this whole area here. We're going to rotate this area around the x-axis or about the x-axis. Look, if you, this looks like this is a triangle in a 2D shape. If we rotate it around the x-axis, we should form something like a cone. We're going to form a cone. Just want to say this so that you get how the reasoning behind it. So we're going to form a cone. So this will be a cone, a right circular cone. It will be like this. See, it will be a right circular cone. This is the area. This is the shape that we're going to form after doing this rotation, and it will be having a radius from here to there. It has a radius r. It will have a height, which is the length from here to there. We call this h. That's it. That's how this cone will look like. It's a cone. So if we can find the volume of this cone, this is one other area that I want you guys to understand, because if the shape is a regular shape, the shape that you know, like a cube or a rectangular prism or a triangular prism or a sphere or a cone like this, a right circular cone, we already have formula for calculating the volume. We don't have a problem with calculating the volume of a cone. It is not an issue. The issue arises when we have some shapes that are very irregular or that are irregular. That is where the issue comes. So from here, before even we do our integration, you can even know the volume that we're looking for, as long as you can calculate the volume of this cone. And I want to remind you that the volume of a cone, V cone, is equal to pi r squared h over 3. This is the volume of a cone. So if we can find r, which is the radius of this cone, and h, the height of this cone, we can actually know the volume before we do our integration. Very important. So I'm going to do that. If you look at this shape that we have, the height from here to there, this height here, is going to be our r. And I can assure you, if x is 3 and this line is called y equals to 2x, it means that this point here, y is actually 6. That would be y there. Y will be 6, which is actually our radius. So 6 is the radius of our cone. So we know that r is equal to 6. What else do we know? This height here, this perpendicular height, this h, is actually the length from here to there. So h is actually equal to 3. So with r and h, we can find the volume of this cone. So let us do that. So the volume of this cone is, so V is actually pi times 6 squared times 3 over 3. So the volume of the cone, or the volume of the shape that we're looking for, is actually 36 pi units cubed, because it's a volume, so it's 36 pi units cubed. This is the answer that we should find. This is the answer that we should find. Now, from here, so we have managed to draw this, the area, we have sketched the area and all of that. And as I said, because it is a cone, I already know the volume of the cone. But we are applying integration here. This is the application of integration. So I'm going to go a little bit further and go and explain this issue of a differential element. This issue of a differential element. I'm going to go to a new page. So let me switch off this. Then let's come here. Once again, I'm going to draw the Cartesian plane. A little bit. So this is the Cartesian plane. And I said we have something like here. Now, after we do the rotation, we're going to have something like this. For the sake of everyone, so this is the side. So this is the side view of this shape. This is the side view of this shape. If you come and you look it from the side of this cone, this is how it looks like. And from the value that we have now, we know that this point here is a 3 in terms of x, so this is our x-axis, and this point here is 0.36. We know this, so if we go here, this is actually 0.6, which means down here this is also minus 6, so this is 3 minus 6. Okay, 3 comma minus 6. This is what we have. Now, just like on the area part, we can have a differential element here and of volume. Look how I'm going to draw my differential element of volume. I'm going to come to this cone. So it's the cone. Please have it in your mind. It's not a flat object. It's a cone. And I come to the cone. I do a slice. See, this is a slice. I'm just going to cut something so thin. It's a thin slice. And if I do that, the thickness of this slice is dx. It's a vertical slice that I made here. So the thickness is actually dx. That is the thickness. Then the height of this, see, the height of this plus of this thin slice, it is going to be 2x. It's going to be 2y, I mean, which means from here to there is going to be a y value. So this is like a radius. Now, for you to understand how it looks like, you should imagine that if you take a cone and you do very thin slices of the cone, what kind of shape do you get? You actually get a disc. What you get is a disc. In other words, it is a very thin cylinder. So this is a cylinder. Let me draw something like a sketch of this, how it will look like. It will be like this. You get something like this. So it should be circular. So you get something like a circle, and then because it is a small thickness, I'm just going to draw. This is a sketch, guys, but this is like a disc. It's a solid disc. This is how it will look like. Now the thickness of this disc, we say is dx, and it has obviously a radius here, r. It is actually a cylinder. This is something cylindrical. So if we're going to find the area or the volume of this cylinder, let us find the volume of this cylinder. So it's V of a cylinder. The volume of a cylinder is pi r squared h. So pi r squared h, where r is the radius and h is the height of that cylinder. In this case, it is actually the thickness. So in our case, this is what we have. This small area, I'm going to call it dV. This small volume, I'm going to call it dV. It is also pi r squared, but our r from here, from the diagram, our r is actually a y, so it's pi y squared. then the height is actually this thickness here, dx. So this is the differential element of volume. This is the differential element of volume. A solid disk. It is a full disk. It does not have a hole. It does not have anything. It's a full disk, which is a miniature or a small cylinder. If we want to know now the volume of this whole area, the volume of this whole cone, we're going to add all these vertical thin slices, all of them from here, from x equals to 0 to x equals to 3, such that I'll say v should be pi, or let me do this, v should be the integration or the summation or the addition of all these small elements from 0 to 3 pi y squared dx, which is like integration pi y squared dx from 0 to 3. We have a formula like this on our formula sheet. We have a formula like this, which is a general formula. Now, so this is how you deduce the expression for the volume of the differential element of volume here. This is how you deduce the expression. And I said, if you now want the volume of the whole shape, you're simply adding these small differential elements, and addition in our case is actually integration. That's what we'll be doing. So this is how we approach. It doesn't matter how the shape looks like. This is a straight line, fine, but even if it's not a straight line, it is the same approach. The differential element here will always be a cylinder. It will be something like a cylinder. If it is not a cylinder, a solid cylinder, it can be a cylinder with a hole inside. If you know how to find the volumes of cylinders with a hole, it can be like that. Anyway, this is what we have here. Now let us move on. Now I'm going to move on to calculate this volume here, this total volume. We know it already that it should be 36 pi units cubed. We know it, but we just have to show that. All right. So let me come here and I'm going to use this board. All right. Now we know that our v, so our v is equal to the integration, is equal to pi integration from 0 to 3 of y squared dx. Look, I want to emphasize this. I always say it in my videos, that if you are integrating with respect to x, your limit of integration should also be x values, which is what we did. They are actually x values. Let me take you back where this is. It's here. No, not here. I mean, it's not here. Yes, it's here. These are our limits of integration from 0 to x. That's how we do it. All right, so let's just come out here. Let's come back here. Yes, our limits of integration should be x values because we're using the x here. Another thing is you cannot integrate in terms of x when you have a y expression here, but we know that y is equal to 2x, so y squared is equals to 4x squared. We know this because we're given this from our question. We have an expression for y. We have it. We're just coming back to put it here. So now it means the v is actually the integration is pi integration of 4x squared. So this is equal to pi integration of from 0 to 3 of 4x squared dx. Now we're going to do our integration. So we have pi here, and if we integrate 4x squared, we get 4x cubed over 3 from 0 to 3. Now let us substitute. If we substitute 0, we get 0. So we're just substituting the 3 only. So our final answer is actually pi 4 by 3 cubed over 3. This part here minus 0, obviously. Then we get our final answer. If we do 4 by 3 cubed over 3, we get 36. It's 4 by 3 to the power 3 divided by 3. We get 36 and we multiply by the pi. So our final answer is 36 pi units cubed. We're using units cubed because it's a volume. This is the answer that we got when we used the formula for a volume of a cone. So we got the same answer. This is how you approach this these kind of questions. I want to repeat something that I said before. I want to repeat it. The differential element, in this case, the differential element of volume. This is going to help you to deduce the kind of formula that you should use. The differential element of volume, it is either a solid disk, it's a solid disk. So it's a solid disk, or it is not a solid disk. It's actually something with a hole. So the solid disk is like a cylinder. This solid disk is actually like a cylinder. So you have two. It can be a cylinder like this. Okay, I'm just trying to sketch a cylinder here, guys. So it can be a cylinder like this with the height dx and a radius here of y. Or it can be another solid disk, which is a cylinder like this. And the thickness here, it will be dy, and the radius will be an x. So this happens depending on how you are rotating it. So if you are rotating it around the y-axis, if you are rotating it about the y-axis, so this is about y-axis, this is about x-axis, then there is where you have something like a washer. I'm going to call it a washer. Call it a washer or a disc with a hole. This also happens, especially you are rotating an area between or bounded by two functions. You are going to have the area is sort of like the volume, the differential element of volume will be a disc with a hole, or what we call a washer. Those who know what are called washers. So how would it look like? It will look like this. So this is if this is the top part of it, and so we have something like this, and then there is a hole here. There is a hole. So from the center, we actually have two. We have a radius of the outer cylinder, or the cylinder outside, and we also have a radius of the inner cylinder. This is where, and the thickness here can be a dx. Now, this is where you're going to find formulas like your r here. Your r in this case would be y1 minus y2. You can have another similar situation where your r will be x1 minus x2. So this guides you in terms of the formula that you're going to use. So for this situation here, the first one, you're going to use the formula that we just used now, that says v is equal to pi integration from a to b of y squared dx. That is what we use. For this, the second situation, your formula will be v equals to pi integration from let's say c to d of x squared dy. So from what I just explained before, that if you're using dy here, it means your c and d are actually y values. Your limits of integration are y values. This is what you get here. Then on this situation here, our v will be pi integration from a to b of y1 squared minus y2 squared dx, the thickness. You see, so these formulas actually, or this kind of reason that I'm giving you, gives you an idea of which formula you're going to choose, because you already have these formulas on your formula sheet. This is very, very important. Now I want to do an example now where we are rotating about the y-axis. I'm going to use my similar question, the question that I used here. This is where we are. I'm going to use this question again, but this time we are rotating our area about the y-axis. Now from here, I'm going to do a sketch of what is going to happen. I'm going to do a sketch of what is going to happen here. Let us draw. Let's draw the Cartesian plane once again. I'm going to use this one. So this is our Cartesian plane, the y-axis, then the x-axis, and I'm going to draw this line here, which is our y equals to 2x. And if we rotate this about the y-axis, this is what's going to happen. So this is our y, this is our x. If we rotate, so the area now that we're rotating, remember this area, this is the area. So we said this is 3, and we said at this point here, y is actually 6. If we take this area here, and we rotate it around the y-axis, what we're going to get is a cylinder. The shape is going to be a cylinder with a hole or something like a cone that has been cut out of that cylinder. This is what we're going to get. Let me do a sketch of that area. It will look like this. It's not the area, by the way. It's actually a cylinder. So it's a 3D shape. From the side, that's how it will look like. From the side, we're going to have something like this. And so this is the top. This is the top of the shape. Like that. And so this point here is like our origin. And then inside, it is going to be, let me use a straight line. So inside, it's going to be like this. This part here and this part are solid. The rest is a hole. That's what you get if you take this area and you rotate it around the y-axis. You get something like this. And then from here we can deduce now. This is a cylinder, by the way. This is a cylinder. Just that we're looking at it from the side. This is the side view of this cylinder. It will be like this. But if you look pick from the top, you're going to see that it looks like you have cut out a cone from that cylinder. It is a hole. Now the differential element here, we are going to cut something horizontally. So let me cut here. I want to cut something horizontally. So I'm going to cut, let me use a blue color. I'm going to draw this. I'm going to cut something like this, a very thin something from corner to corner, or from end to end. If you look at what I have here, it is a disc. It is a disc, and the disc has got a thickness of dy. That is the thickness of the disc. However, it is open in the middle. It is open in the middle, such that it has an outer radius and an inner radius. From the center here, so this is the center of this disc. From here to there is an x value here. Let us call that x1. Then from here to there, we have another x here, a radius. This is an x radius. So this is our x2. Now, if we are going to find the volume of this small disk, let me write it. The volume of this small disk, which is our differential volume, it is dV. dV will be equals to volume of the outer cylinder minus the volume of the inner cylinder. Remember, you carved out something. So if I'm going to do that, it's like pi x1, which is our radius, x1 squared. x1 squared d dy minus pi x2 squared d dy. This should be our differential volume element. So this is the differential element of volume from this disk that we get in this situation, which actually tells us that dv, if we do some algebra here, which means factorizing and all of that, it means we're going to have pi x1 squared minus y1 squared. So x1 squared minus x2 squared d dy. So this is the kind of formula that you're going to use. In fact, this whole tells you about what I just explained previously, that you have to understand your differential volume element so that you can make a good choice about the right formula to use. So now I have the right formula to use. In this case, my x1 is actually 3. My x1 is 3 because every time you move from this to the extreme of this shape, you encounter a 3. That's your x1. So my x1 is actually 3. My x2, so let me draw a line here. So from here to there, this is a radius. This is my x1, which I get it from here. So x1 is equals to 3. Now x2 is from here to this line here, which means x2 is going to come from the line y equals to 2x. This is your x2. From here we know that x2 is equals to y over 2. Done. So x1 is 3, x2 is y over 2. If we take this and we put in that formula, then we can find our volume, the volume that we get if we rotate the area about the y-axis. That's what we're going to do. So let me move on. So I'm going to go to a new page and do this calculation now. So let us put this off. So we're here. dv, let me write what you have. dv is pi x1 squared minus x2 squared d dy. And we can agree that x1 is equals to 3 and x2 is y over 2. We just put in here. Then when it comes to the limits of integration, we're going to get our limits of integration from our diagram. So the diagram is going to give us our limits of integration. Let me show the diagram. So this is our diagram here. This is our diagram here. So our limits of integration are going to be y values because our differential volume element is actually horizontal. So these are going to be y values. So we're going to be integrating from y equals to 0 to y equals to 6. That's what we're going to be doing. So let us do that. So let's come here. So our limits of integration are that. So to get v, so v is actually the integration. So we can take pi outside. The integration from 0 to 6 of x1 squared, which is 3 squared, so it's 3 squared, minus x2 squared, which is y over 2 squared, minus y squared over 4. We are integrating this with respect to y. I did things a bit faster here. One, I'm integrating with respect to y. So my limits of integration are y values 0 and 6. And in here, in the bracket, I have functions or I have expressions that are in terms of y, so I can integrate them easily. So this is like pi, we integrate 9, we get 9y. So this is 9y minus, if we integrate y squared over 4, we get y cubed over 12 from 0 to 6. Now, so this is actually pi times, okay, we put in 6 first, so it's 9 by 6 minus 6 cubed over 12 We close this. Then, no, I don't have to close that first. Let me use a green pen. So this minus 0, I'm minusing 0 here because if you substitute 0 into that expression, everything becomes 0. So let's come here. Now we can close the bracket. So we pi what is inside the bracket. So it's 9 by 6 minus 6 cubed over 12. We get 36 pi, so we get 36 pi units cubed. All right, guys, this was just coincidence that when we rotate the area around the x-axis, we got 36 pi units cubed. And when we rotated it around the y-axis, we got pi units cubed. It was just coincidence. Don't go around and say, oh, it doesn't matter whether you rotate it around y-axis or x-axis. No, it really does matter. This was just coincidence, but the approach is what is important here, especially the concept of a differential element of volume. This concept here is a very, very powerful concept because it helps you choose the right formula. It helps you understand if your differential element is a solid disk or it is a disk that got a hole. In other words, the whole shape that you're going to get, is it either a solid shape, fully solid, or it is something like a shell, a shape that has got a hole or an opening inside. That this is what you get by understanding what we call the differential element. I'm going to do other examples where I explain how to get this volume. It's a very powerful concept. It's a very important concept. Yeah, but for now, thank you for watching the video. If you have any questions or any queries, just write in the comment section below. Give the video a thumbs up and subscribe to the channel. Otherwise, thank you.